12.6 chiral molecules. Notice they have all these pictures of hands here and a mirror, and you may go, what does that have to do with anything? Well, chiral is from Latin and it means handedness. Notice your right hand is the mirror image of your left hand. So let's go back in time a few chapters ago when we were talking about isomers. Molecules are structural isomers when they have the same molecular formula but different bonding arrangements. For example, ethanol and dimethyl ether, granted, they both have 2 carbons, 6 hydrogens, and 1 oxygen, but we know they have total different properties, and you might want to drink some ethanol, but you certainly wouldn't want to drink any ether, okay? So they're totally different. Now, stereoisomers do have identical molecular formulas, but they're not structural isomers. In stereoisomers, the atoms are bonded in the same sequence, but differ in the way that they are arranged three-dimensionally in space. When stereoisomers have mirror images that are different, they are said to have handedness. So let's learn all about that. Chiral molecules have the same number of atoms arranged differently in space. They have 1 or more chiral carbon atoms, each of which is bonded to 4 different groups. So this is how you can tell if a molecule is chiral or not. Look and see at the groups around that one particular carbon and see if there's 4 different groups. If there are, it will be a chiral molecule. So think of your hands, handedness. Your left hand will not fit into a right hand glove, and your right hand will not fit into a left hand glove. Here are some other examples of everyday chiral and achiral objects. Now, achiral means without handedness. So, chiral, you have gloves. Chiral are shoes, while your left foot is not going to fit into your right shoe. Okay? Your scissors, those 2 blades, if you superimpose them, they're not superimposable. They are mirror images. Okay, that's why it actually works. A screw is an example of that. Whereas a glass is achiral. It does not exhibit handedness, or our soccer ball there. Now, mirror images of chiral compounds cannot be superimposed. So let's look at this example of a chiral compound right here. So first of all, we know it's chiral because here's our carbon atom, and we have 4 different types of groups attached to it. So it's chiral. Now then, let's take another atom that has carbon with 4 of those same exact groups, but let's change the way that we arrange them in space so that they are mirror images. So they're mirror images, but then when we try to put them and superimpose them, they are not superimposable, which means they're not going to fit into the same receptor site, which means they're going to act differently than another one. So this molecule in the back will act differently than this molecule in the front. Achiral structures are superimposable. So if it's without chirality, if it's not a chiral object, it's superimposable. Let's look at example here. First of all, we know this is an achiral structure. Why? That means it's without handedness. Why? Our carbon here has a chlorine, a hydrogen, and it has 2 groups that are the same. So then it's not chiral. And you can attest that because then its, quote, mirror image, which it doesn't have one, is exactly the same molecule as it. So let's see if you can identify which of these are chiral or which are achiral. Press pause and come back. Well, we looked at this one. This carbon has 4 different groups attached to it. It has a chlorine, a hydrogen, a methyl, and an ethyl. So it is chiral. This B is not chiral. It is achiral. Why? Because this carbon has 2 items that are the same. It has a hydrogen and a hydrogen. Oh, right there, not chiral. Okay, number C is chiral also because it has 4 different kinds of groups around the carbon. All right, Fischer projections. It's a 2-dimensional representation of a 3-dimensional molecule. So let's try to help you visualize this. They put the most oxidized group at the top and so forth. So let's look at our Fisher projections here to try to help you visualize. So this bar here represents the chiral carbon. So this carbon right here represents this spot right here on our Fisher projection. So that's an important thing. Now, let's see what's so important about that. Let's look at the second to last carbon, which is this, next to this alcohol group. So it's the second to last carbon here. And see which side this OH is in relationship to the H. And so if the OH is on the left, it is designated as L. So this molecule is glyceraldehyde, so this particular one is going to be L-glyceraldehyde. Whereas if we look at the mirror image, this enantiomer, the OH is on the right-hand side of this chiral carbon, and so that is D-glyceraldehyde. So if the OH is on the left, it's L. If the OH is on the right of this chiral carbon, it is designated as D. So go look in your cupboards. If you have, or your medicine cabinet, see if you can look at something and find something that might have like D something something or L something something. Like I sometimes take L-lysine. Take a guess what the L means. Well, that's totally referring to this position right here. The L is on, the OH is on the left-hand side. So indicate whether each pair is a mirror image that cannot be superimposed. Okay, here we go. All right, we have these 4 groups that are different, and then this look, and so this is a chiral molecule. Now then let's look and see. Yes, this is a chiral molecule, and yes, this is the exact mirror image. If I were to draw like a mirror right here, I could see that they are a mirror image. B, though, first of all, it's not chiral because this carbon has 2 items of the same on it. It has 2 hydrogens. So because it's not chiral, then it cannot have a mirror image. So even though you might think, oh, this looks like a mirror image, by definition, if it is not chiral, if it is achiral, it cannot be superimposed. It has to be chiral in order for this to be this mirror image. Otherwise, when you try to put them on there, you'll see that they're exactly the same molecule. So if I said something wrong there, oh well. So here's our concept map. I want to bring out a couple of ideas and a couple of items about the importance of the chiral molecules. And so you should go into the chapter and read that section. And it talks, one of the things it talks about is L-DOPA. And so with our L-DOPA, yes, of course, that refers to what side the item is, the OH is, in relationship to the rest of the bottom chiral carbon. So let's, one of the enantiomers is used to treat Parkinson's disease, whereas the other enantiomer contributes to side effects. So the concept there is, you can help cut down on the side effects if you can have this pure substance. If you have it where only the particular side that works is given to you. So ketamine, for example, one enantiomer is 4 times more potent as an anesthetic, whereas the other enantiomer produces more side effects. Okay, L-methodopa, actually one of them is effective in treating hypertension, and the other contributes to side effects. Amphetamines, one of the enantiomers is 3 to 4 times more potent as a stimulant, whereas the other enantiomer not only doesn't act as a stimulant, but it's the one that produces the more adverse cardiovascular effects. Thyroxine, one of the enantiomers, is prescribed for thyroid deficiency, whereas the other enantiomer decreases your serum cholesterol. So we could go on, but I'm hoping you see the importance of, as time goes on, to be able to separate these enantiomers. Because your body has certain receptor sites, and certain receptor sites are going to only take and work with certain enantiomers. This is kind of something that's really important in our medicine field, and for if we want adverse side effects or whatever for our bodies. Anyway, I'm hoping that the chiral molecules will be of interest to you.